So the effect that you've been seeing is what's called self-inductance. Mutual inductance occurs between two coils of wire. Everything that we've seen here is just for a single coil of wire. And let's just see what's been observed. Firstly, when you connect up the coil tends to prevent current flow initially and then gradually allows the current to go through. Secondly, when the coil was switched on and then it was switched off, the current tends to stay in the coil until it eventually dies down. So the way that it works is if you draw out a circuit for, if that's coming from the power supply here, and we're taking the current from here round a coil of wire like that. So that's, you can imagine it going round and round and then back like that. As soon as you try and switch on the current, because we're using right hand, remember, the motion of the electrons is that way. That means you're gripping with left hand, I'm using the left hand rule. Because the motion of the electrons is that way and you're gripping around that way, it's going to cause a magnetic field going into the page over here. As it comes down that way, again it's going to be curving round, and again it's going to be going into the page on that side. So we've got a magnetic field going into the board like that. Now, this is the key thing. Because you've got an increasing magnetic field around a coil, what effect is that going to have on the coil? Think about what we were doing before. It'll induce a voltage, okay? So we've got increasing magnetic field, coil of wire, induced voltage. Now there's only two ways the induced voltage could move the electrons. It can either try and move them that way, or it can try and move them in reverse. By conservation of energy, if you had to sort of take an educated guess, which one would you go for? Yeah. Otherwise, suddenly we've found a way to invent energy and create energy if the change in magnetic field caused that to go around that way. So in practice, it works out that you are getting what's called a back EMF. But what the law of physics actually says that they do actually end up being pushed back the way is what's called Lenz's law. Lenz's law says that when any change acts on a coil of wire, the coil of wire exerts a change to oppose that. So it actually produces what's called a back EMF. So we just put in beside here. So this is an inductor, a coil with DC. So the direction of an induced EMF is such that it opposes the change producing it. So it's a bit like this coil of wire has its own internal battery that suddenly sets up in opposition to the applied EMF. The value of that internal or back EMF is actually equal and opposite to the EMF which has been externally applied. In terms of what happens after a while is, because this back EMF doesn't have any real energy, it's just a sort of knee-jerk response to this initial rush of current, what happens in time is that the current does tend to overpower that, and you do get current flowing. So overall, you would end up with a current flowing through a coil, but it might take a fraction of a second, which is what we observed before. The inductance of the coil itself is actually a measure of how well that change of current how long that change in current tends to take there. So if you plotted which we will be doing later on today or tomorrow afternoon, if you plot the current against the time for the inductor, what you'd find is the current tends to take a while to warm up and then finally reaches the current value that you would expect if you've got the resistance of the coil, the voltage across it, you would get that voltage divided by the resistance of the coil. So you will end up with the proper current, but it takes this time to do that. And this is because at this point, there's a back EMF which is opposing the power supply voltage, ending up with zero current flow at that particular time. As soon as you switch on, no current flows because the back EMF opposes it. This rate of change of current initially, which you can plot from a graph there, if that's the current there, you can get that rate of change of current just by the gradient of that graph, di by dt, the rate of change of current. That gives you how quickly the current takes to increase. Faraday's law of induction says that you can get the inductance L of the coil is defined as being the constant in the equation where the back EMF from the coil is equal to minus L, the inductance, times the rate of change of current, di by dt. Okay, so that's the back EMF, which is going to be equal to the power supply when you switch on. At various stages up here, the change in current will be less because the back EMF will be less. That's the inductance. Inductance, Chris, can you remember the units for it? Yeah, it's measured in henries. And I should have seen and get a photo of whoever Henry was. And that's in amps per second, which is the rate of change of current. EMF would obviously be in volts. There's a negative sign in here. Why is there a negative? Yeah, it's an opposing EMF. So it's tending to oppose the change producing it. So what we're going to set up is this coil of wire using the Dr. Dack setup there. Try and see if we can get this growth of current in a DC inductor circuit. Can we measure that rate of change of current and then see if we can work out the inductance if we know the rate of change of current and we know the back EMF at the initial switch on, which would be equal to the supply voltage.